In this video, I'd like to share a proof with you of the Pythagorean theorem. And this proof of the Pythagorean theorem is actually due to President Garfield. So this is James A. Garfield's proof from 1876, just a few years before he became president. So James A. Garfield proof from 1876. Here's what President Garfield decided to do to try to prove the Pythagorean theorem. The first thing he did, well, that we're going to do at least, is to sketch a right triangle. Now, the only thing we need to make sure of is that we have a right angle here. All right, so here's our right angle. Let's call this side A, this side B, and this side C. And what we can do then is we can take the same, we can draw a congruent triangle, right triangle, but this time we can make sure that the longer side, the longer leg, is down here, and make this be a straight line. So I'm going to say that's about B, and this is about the height of A. And so now we'll just pretend that these are the same, but I'm going to write that they're the same. So that's a right angle. This will be C again. This one will be B now, and this will be A. And at this point we can complete, by connecting these two vertices, these 2 points, we can complete the trapezoid. Alright, so we can look at this trapezoid right here. Now, let's look at a couple other things before we write down the proof of this. This angle of the triangle is congruent to this angle down here, right? Just by congruent triangle properties. This angle right here, this is angle capital B if we're going to name it, but we're just going to work with the side lengths, but this angle is congruent to this one, right? And so what that means then, if we look at this, we have a straight line segment here, right? And these angles then have to add up to 180 degrees. The blue and the red, because the blue and the red, so notice I've color-coded this so we can easily tell what angles are what, because those are angles in a right triangle, right? Those also have to add up to 90 degrees. All right, so blue plus red has to equal 90 because of the triangle. Blue plus red, again, has to be 90 because of this triangle. And that means that blue plus red over here has to equal 90. And so that means that actually this is a right triangle. All right, this triangle that is built from the side lengths of C, that's a right triangle as well. All right, at this point, what we can do is we can compute the area of this trapezoid 2 different ways. Okay, so let's recall the area of a trapezoid. If we just have a generic trapezoid, we can just even make it. Trapezoid has to have parallel sides, so these two are parallel, right? But here's a trapezoid. There's an altitude. That's a height h. It's supposed to be the same as this one. All right, my picture's not so great. But the idea now is that if that's the height, then there's one base, and there's another base. So this is like B1 and B2. And the area of this trapezoid is the height, which is, again, it doesn't look like it in the picture, but it's the same. Okay, so the area here is the height times the average of the 2 bases. So that's B1 plus B2 all divided by h. Okay, now when we look at this trapezoid, what are we going to use? We're going to use this side to be the height, actually, and these 2 sides to be the 2 bases, base 1 and base 2 from our picture. Okay, so on one hand, the area of the trapezoid is the average, so this I wrote an h here, sorry, I said average, so it's over 2. So on one hand, the area of the trapezoid, the given trapezoid that we built out of our right triangles, it's the height, which is a plus b. This length is a plus b, right? So there's a plus b, times the average of the 2 bases. Again, this is all kind of turned on its side, right? But the average of these 2 sides is a plus b divided by 2. So a plus b divided by 2. So that's the area of this thing. If we multiply this out, we end up with 1/2 times a squared plus 2ab. So if you just distribute everything out here, you have a squared, ab. So that's 2ab plus b squared. All right, and that's the area of the trapezoid. Now, there's another way to compute the area of this trapezoid, and that's to do it in pieces, or by parts, you might say. And so what we can do, I'm going to switch to highlighter here, we can just compute the areas of these right triangles, and then add them up, right? We can add these up. So the areas of the right triangles, when summed together, has to equal the area of the trapezoid because that's the shape that it adds up to, right? And at this point, the area of the trapezoid done a different way now. So this time it's done by triangles. This time it's going to be what? Well, there's two copies of these ones. The area of a triangle is 1/2 base times height. These are right triangles, so it's 1/2 leg times leg, right? So on this hand, it's going to be 1/2 a times b times 2. There's two of those, right? So we'll write it this way. It's 2 times 1/2 a times b. All right. Plus, then we have to add in the area of the magenta shaded one. That one's a right triangle whose side lengths are both c. So that's going to be plus 1/2 c times c is c squared, right? So this is equal to the area of the whole shape on one hand. This is equal to the area of the whole shape computed another way. If they're both equal to the area of the entire trapezoid, they must be equal to each other, right? So these two are the same number, the same area, and that means everything else here has to be equal to each other. And so what we can do then is set them equal, right? So we have setting these equal. Here's what we have. We have 1/2 a squared plus 2ab plus b squared equals 1/2. I'm going to factor out this 1/2 actually, okay? So I'm going to take this 1/2 all the way out, factor it out, and write this as 1/2 times 2 still there, so 2ab plus c squared. All right, and at this point we can start canceling stuff. We see the 1/2s. The way I've done it, and the reason I did it, is because those 1/2s cancel. And once the 1/2s are gone, then the 2ab's cancel. So 2ab cancels with 2ab. All right. And then what's left? Right? What's left is a squared plus b squared on the left-hand side and c squared on the right-hand side. And so this is President Garfield's proof of the Pythagorean Theorem. I've read in a Mathematical Association of America journal that this was his proof. I'm not sure though if it was originally his idea or if he just wrote it up and somebody heard about it, but it's pretty cool though that a president of the United States was able to prove the Pythagorean theorem in a way that's so geometrically clear and easy to understand. You could cut out triangles like this with some students and actually show that this proof works geometrically, right? And you get this algebraic formula from it, and it's a beautiful, beautiful thing.